So let's say when we discussed about the electron-electron interaction, I presented you the calculation of the contribution of the electrons to the dielectric constant of the system, and that contribution could be given by the electrons, as the electrons are mobile particles that may rearrange their configuration, their position, depending on the presence of external fields, or have recently allowed the ions to move with respect to their equilibrium positions. This motion is not as fast and as wide as the one that can be displayed by electrons, but in any case, also the ions may, let's say, rearrange their configuration depending on the presence of external charges or external fields. So what one expects is that the full dielectric constant of a system should depend both on a contribution coming from electrons and from a contribution given by the ions. So the idea is to, let's say, write the relative contribution of, let's say, write down an equation for the relative permittivity contribution to the determination of the value of the actual potential, this V total, that is that corresponds to, let's say, the presence, for instance, of the potential of an external charge that is represented by phi external. And in this expression, sorry, in this value for E, one expects to, let's say, include again both the contribution of ions and the contribution for electrons. And now all the equations that I will write down are equations that are not in the real space, but equations in the Fourier space, as we did in the case for electrons. So in this case, we expect to concentrate both on the electrons contribution and the ions contribution to the relative permittivity. Just one comment: when I say electrons, we in generally one considers electrons to be the let's say free electrons or the electrons that participate to the metallic bonding. So when you say electrons, you do not include the core electrons. So electrons that are strongly bound to the system are not represented by the category electrons in this case. At the same time, when I say ions, I do not mean just the nucleus of the atom, but I mean the nucleus of the atom plus the core electrons. So the electrons that are strongly bound to the ions and that do not participate to conduction. So making this distinction, there are a group of electrons that are strongly bound to the ions and that do not participate to the electron contribution to the dielectric constant. And in this case, electrons and ions are two populations of charged particles, and one represents a contribution for an external potential with respect to the other one. So electrons are external charges with respect to the ion system, and the ions are external charges with respect to the electron system. So we may say that let's say, when we consider the electron contribution to the screening effect, the electron contribution has to screen both the external potential and the ion potential. So in this case, we just write down the fact that for the electrons, the external charges are both the external potential that is represented by an additional charge or electric field that we apply to the system, plus the ion contribution. And the same is fine for ions. So the ion contribution is meant to screen the external potential and the electron contribution. If we sum those two equations, we have that the contribution of the electrons plus the contribution of the ions times phi total is equal to phi external plus phi external plus phi electrons plus the potential of the ions. This term here is the external potential plus the contribution of the electrons plus the contribution of the ions. So this is the full potential into the system, because it's the external one plus the effect that is due to the other two charges, other two system of charges that we have in the system. So due to that, we have that contribution of the electrons plus contribution of the ions minus 1 times phi total is equal to the external contribution, to the external potential. So in this representation, the relative permittivity of the system is the electronic one plus the ionic one minus 1. What at this point, one additional step can be done, and is the following. If you consider ions, ions means nucleus plus electrons that are rigidly bound to the nucleus. In general, if you stay, let's say, outside the solid, it's difficult to interact directly with ions, because to access ions, you have to, let's say, overcome the cloud of electrons that participate to the metallic bonding that screen the contribution of all the ions. So in general, this expression is not written down just in terms of the ion contribution, but in terms of what is called dressed ions. What is the meaning of dressed ions? Dressed ions means the ion, so nucleus plus rigidly bound electrons, plus the, let's say, conduction electrons that interact with that ion. So during its motion, the ion changes its position, and as the position of the ion changes, the electronic cloud that is close to that ion changes configuration, so to fulfill the requirement, so to take into account what is of the actual position of that ion. So the idea is, as it is difficult to access what a single ion is doing, because the ion moves along with the cloud of electrons that are close to that ion, then it's better to express the relative permittivity not as a function of just the ion contribution, but as a function of the dressed, let's say, ion contribution. How is it possible to, let's say, rewrite the general equation, such as this one here, considering this contribution of conduction electrons and dressed ions? So if we have the total potential, if we now concentrate on the dressed ions, if we concentrate on dressed ions, what is their contribution regarding the screening? Their contribution is the following. So if we focus on the electrons that are, let's say, this sort of glue that keeps the solid in equilibrium, they have a double role. They have this role, that is, if you apply an external an external potential to the system, the dressed ions may change their configuration depending on the time dependence or the position dependence of that external potential. But let's say, when the dressed ions have to interact with this potential, the dressed ions do not interact directly with the external potential, because the dressed ions are surrounded by by this cloud of let's say conduction electrons that may rearrange their configuration depending on the external potential. So the idea is that when dressed ion screen something, they do not screen directly the external contribution, but they screen the external contribution after that is screened by the electrons. So the electrons in this case have a double role. One role is to screen the external potential. The other one is to change their configuration depending on the specific position that is displayed by the ions. So in this picture, the electrons have again two roles. One role is the screening of external charges. The other role is their reconfiguration depending on the exact position of the ions. So due to that, we have that the relative permittivity is equal to the dressed ion contribution plus the electron contribution. And if we compare this equation and this equation, they have to be the same equation. Sorry, not the same equation, but they have to give us the same expression. So at this point, we may say that the relative permittivity is the electronic contribution times, if we now collect in this one here, if we collect the electronic contribution, we have then 1 plus E ions minus 1 divided by the electron contribution. So this is the dressed ion term. So the electronic term is the one in front here, and this is, in comparison with this equation, this represents the dressed ion contribution. At this point, the problem is to find an expression for this, that is the ion contribution. So at this point, the question is, how may we estimate the relative permittivity of the ions? If you concentrate, to answer that question, you may concentrate on the ionic system. The ionic system is, let's say, not strictly uniform, but is a background of positive charge that you have in the system. And we have just discovered by studying phonons that background is able to display oscillations. So you have a nearly, let's say, not strictly uniform, but a nearly uniform background of positive charge that may oscillate depending on possible perturbation, interaction with the electrons, and so on. We have already had the opportunity to consider the oscillation of a system that was nearly uniform in distribution, a system of negative charges, and we found that when I presented to you the Drude model. In that case, the electrons were considered to be a sort of uniform background of charge in the system, and they were able to display oscillations. In that case, we were able to evaluate the relative permittivity of the electrons, and we found that so when we consider the Drude model, we had that the relative permittivity of the due to the contribution of the electrons was equal to 1 minus omega squared the square of the plasma frequency divided by the square of the frequency. And the square of the plasma frequency was n, where n is the electronic density times E squared divided by E0 divided by the mass of the electron. So the idea is, if we do not concentrate on, let's say, at this point, sorry for this short break, the question is, may we use the same result to describe the oscillation of the ions in the system? The answer is nor yes nor no, because that depends on the wave vector. We know that the ions oscillate in the system, and they may display long-range oscillations and short-range oscillations. If we consider long-range oscillations, then for long-range oscillations, you may suppose that the system of positive charges that is due to the ions is nearly a continuous and uniform. So if we consider long-range oscillations, then this approach may be fine. But if we consider short-range oscillations, that means where the lambda, the wavelength of the oscillation, is comparable to the size of the lattice, then at that point you may not consider the ionic system to be uniform and continuous. So the answer is for long-range oscillations, so if k is large, if k is small and the wavelength is large, then we may approximate the ionic contribution to the dielectric constant with the result that we have used for electrons. So the point is, we may use the relative permittivity that we obtain for the with the Drude model can be used to describe long-range oscillations of the ionic system, of the ions. So long-range oscillations means small values of k. So the center of the Brillouin zone. The central part of the Brillouin zone can be well described by this approach. So what we need to do now is just to replace the value of omega square of plasma, because in the case of the ions, we have to say that n is the ionic density. E squared is the square of the charge of the ion. Then E0 is E0, and then we have the mass of the ion. We may try to write that as a function of the plasma frequency for the electrons. So Ni is the electronic density divided by Z. Then we have Za squared divided by E0. Then at this point, we need the electron mass. So we may multiply and divide everything by the electron mass. So at this point, we have that electronic density. We have the square of the charge here, E0 and M are the plasma frequency value that we obtain for electrons. Then we have Z, one Z here, because one of the other Z is simplified with the Z that we have the denominator here for the positive charge of the nucleus. And then we have the ratio between the electron mass and the ion mass. So at this point, we may say that the ion's contribution is equal to 1 minus the square of the plasma frequency of the ions divided by the square root of the frequency. So what we have here is 1 minus omega square of plasma evaluated for the electrons times Z electronic mass divided by ionic mass, everything divided by the square of the frequency. So at this point, we have an approximation for the ionic contribution to the dielectric constant. The next step is to evaluate this parenthesis, so to evaluate the dressed ions contribution. So for the dressed ion contribution, we have 1 plus 1 divided by the electronic contribution. Now, electric constant of the ions minus 1 gives us just the minus omega squared of plasma, zeta, the positive charge of the nucleus, electronic mass, divided by the ion mass, everything divided by the square of the frequency. So we have 1 minus omega squared of plasma, Zm divided by the electronic contribution to the dielectric constant divided by omega squared. Now, please note this point because it's an important point. What is wrong? Is there something wrong with this equation? So, is there something wrong with the E-ion contribution? So, what is wrong with that term there? The plasma frequency, in principle, is the equivalent of the phonon frequency because plasma oscillation is an oscillation of let's say, of a system of charges, and what, let's say, the ions, the lattice is a system of charges that may oscillate. So, in principle, the plasma oscillation should be the equivalent. Sorry, the plasma frequency should be the equivalent of the phonon frequency. But we know that for small values of the wave vector, the phonon frequency goes to 0. Differently, the plasma frequency is a fixed number, so no wave vector dependence. Why is that? Because if you remember, when we, let's say, when we discussed the electronic oscillation into the system, we said, okay, the electronic system may oscillate with respect to the ground of charge that is given by the ions. So they may move back and forth into the system. But if a system of charge moves in this way, so you have a uniform oscillation, this means that all the charges know what happens to all the other charges in the system. So you may, at this point, you expect to have long-range forces. Long range means that every charge in the system knows what happens to all the other charges in the system. But if you remember, the linear dependence of the frequency of the phonons for small values of k was due to an approximation where we assumed that actually this was not the situation, because we said, okay, in principle, the interionic forces have a very long range, but we have to consider the electron screening. So due to the electron screening, the range of interaction of interionic forces is not infinite, but is reduced to, let's say, to a shorter length. And if you notice here, what we have is that in this ratio, the omega squared of plasma is divided by the dielectric constant of the electrons. If you remember the spring mass problem, in the spring mass problem, the frequency, the square of the frequency, so if you consider the spring mass problem, the square of the frequency is related to the constant of the spring, K, divided by the mass of the sample that you connect to the spring. K is proportional to the force. So K is an indication of how strong the force is. So you may consider that the square of the plasma frequency is related to the force that, let's say, acts on the charges and let those charges oscillate back and forth into the system. So if you give to the square of the plasma frequency the meaning of term proportional to the force acting on the charges, then if you divide by that force, or in this case, the square of the plasma frequency, by the dielectric constant of the electrons, is just like as if you were saying, okay, the force acting on the charges has not an infinite range, but has a shorter range that is due, and this shorter range is due to the contribution of the conducting electrons. So this ratio, omega square of plasma divided by the electronic dielectric constant, is very important because it's a sort of inclusion into this calculation of the fact that the forces acting on the different charges that you have in the system, in this case the ions, are not infinite range forces, but are short range forces, because due to the electronic contribution, the range of interaction of the charges is strongly reduced. So it's an important step of the calculation. And in this case, I just rewrite that so I may go on with the rest of the calculation. So we have that the dressed ions, our contribution is 1 minus omega square of plasma, the electronic contribution, Zm divided by the ion mass divided by the square of the frequency. If we now write the expression for the, let's say, the dielectric constant of the electrons was 1 plus K0 squared divided by K squared. So in this case, we have that this is equal to 1 minus square of plasma frequency. Then we have K squared plus K0 squared. Then we have a K squared up here. Then we have Zm divided by ionic mass, 1 divided by the square of the frequency. Now, if you look at this expression is square of plasma frequency of the electrons. So for if K is small, what happens to that expression? That expression becomes omega squared of plasma, K squared, Zm divided by the ionic mass. At the denominator, you may neglect K squared with respect to K0 squared, so you have just K0 squared. So this is a sort of plasma frequency of the ions that depends on the wave vector, because we have K squared here. And if you notice, the square of the frequency is proportional to the square of the wave vector. So in the low K limit, the frequency and the wave vector are directly proportional with each other. So, and this is exactly what we found for phonons. So for phonons, the frequency is proportional to the wave vector. And due to that, we have that we may compare this expression to the expression that we found, for instance, in the Debye model. the Debye model, or in general in the linear dependence that we have very close to the origin of this of the first Brillouin zone, we have a linear dependence of the frequency on the wave vector. So we have that the square of the frequency is proportional to the square of the wave vector, and the proportionality coefficient is the square of the speed of sound within the solid. So at this point, we may write down this equation that tells us that the square of the speed of sound within the solid is equal to the square of the plasma frequency divided by k0 squared times Zm divided by the ionic mass. So due to that, we have the opportunity to find a new way to, let's say, evaluate the square of the speed of the phonons within the system using this approach. And just to tell you what happens, so c squared is equal to omega squared of plasma, so electronic density E squared divided by E0 electronic mass times 1 divided k0 squared times Zm divided by the ionic mass. At this point, what is k0 squared equal to? If you remember the calculation we did, k0 squared was equal to E squared divided by E0 times the derivative of the electronic density at equilibrium with respect to the chemical potential. The derivative of the electronic density with respect to the chemical potential is equal to the density of state at the Fermi level. So this is equal to E squared divided by E0, and the density of states at the Fermi level is the 3 divided by 2 times electronic density divided by EF. So if we replace that, we have that electronic density times E squared times E0 electronic mass, then we have Zm divided by the ionic mass. K0 squared is E squared 3 electronic density, then we have E0 times 2 times Fermi energy. We may simplify this term and this term, this term and this term, this term and this term. Then we may also simplify E0 and E0. So what is left here is 2 divided by 3 times Z divided by the ionic mass. And then we have the Fermi energy. Since on this side here we have the square of the velocity, it would be nice to have a square of the velocity also on the other side. And if we use the, let's say, free electron expression, then EF is equal to 1/2 mass of the electron square of the Fermi velocity. So at this point, we may simplify 2 and 2, and we have that c squared is equal to 1/3 Z times electronic mass divided by ionic mass times Fermi velocity squared. And if you notice here, on this side, you have the speed of the phonon in the system in the low K approximation. On this side, you have the speed of the electron at the Fermi energy at the Fermi level. The coefficient is Z, that is in general of the order of unity, 3 again of the order of unity. Ratio between electronic mass and ion mass. This ratio is at least of the order of 10 to the minus 3, 10 to the minus 4, because the mass of the ion, let's say the mass of a single proton or a single neutron, is nearly 3 orders of magnitude larger than the mass of the electron. But in the nucleus, we have in general many neutrons and many protons. So this ratio here is of the order at least of 10 to the minus 4. So even when we make the square root, we have that there are 2 orders of magnitude between the speed of sound, the speed of the phonon in the system, and the speed of the electrons at the Fermi energy. So this is another confirmation of the fact that the speed of the phonons in the system is lower and lower with respect to the speed of the phonons, to the speed of the electrons in the system. And this relationship here is called the Bohm-Staver relationship. So this is an equation that relates the speed of the phonons and the speed of the electrons, just going through this approximation where we use the picture of the dressed ions, and we try to build up the frequency, the frequency dependence of those of the dressed ions by starting from the let's say ions contribution and then applying the screening that is given by the electrons. So at this point, we may say that the dressed ion contribution, just to summarize, is 1 minus this square of a frequency that depends on the wave vector divided by the square of the frequency. So we have the square of this plasma frequency of the ions, the dressed ions, depending on the wave vector, divided by the square of the frequency of the external perturbation. So we have the opportunity to write down the full permittivity of the system, that is permittivity of the electrons times permittivity of the dressed ions. So this is the full expression of the relative permittivity of the system in this long wavelength or small k values approximation. So the idea is to say what happens to the, let's say, we have seen what happens to the electron-electron interaction just considering the first term. So just considering the fact that the potential, the interaction potential is not the Coulomb one, but is the Yukawa one. So we have already seen what is the effect of that. The question now is, what happens if we also consider the contribution of the ions? So what happens to the electron-electron interaction, going back to what we have seen at the end of the presentation of the Hartree-Fock approach, if we include this additional term within the calculation. So at this point, the question is, how is it possible to relate the details of the of the relative permittivity to the details of the electrons that are interacting within the system, taking into consideration this specific expression for the permittivity? The answer is the following. If you remember, when we evaluated the total energy due to the electron-electron interaction in the system, we made a calculation where we had there was a sum of so Hartree-Fock approach. We wanted to obtain the energy value corresponding to the interaction between all the electrons, and in that case, the idea was to estimate the contribution of the exchange term. In that sum, we made a summation like this one here. So we summed up K was the wave vector of one electron, M was the wave vector of all the other electrons that were interacting with the electron having wave vector K. So in this case, in the evaluation of the interaction energy, we included let's say, this is the Fourier transform, or is quite close to the Fourier transform of the pure Coulombian potential, because the first calculation that I presented to you was done using the full Coulombian potential. And if you notice here, in the Fourier transform of the Coulomb potential, we use M minus K, that is the difference between the wave vectors of the electrons that are interacting. So the idea is, if I want to use, if I want to apply now this full expression for the dielectric constant to the interaction between the electrons, I have to replace K by the difference between the wave vectors of the electrons that are interacting. So if I have electron 1 and electron 2 that are interacting through this dielectric constant, then one will have wave vector Q1, one will have wave vector Q2. I replace, so the effective potential, the Fourier transform of the effective potential will have a term that is inversely, we have 1 divided by Q1 minus Q2 squared, and this is the pure Coulombian potential. Then we have to divide by the dielectric constant of the system. In this case, we have the electronic contribution, and the electronic contribution gives us Q1 minus Q2 squared plus K0 squared, and up here we have an additional Q1 minus Q2 squared. So we may simplify this, and as we have observed before, we are just left with the Q1 minus Q2 squared plus K0 squared. So this is the effect that we have already seen when we have obtained the Yukawa potential. Then, how do we handle the phonon contribution? In this case, we have to, let's say, we know what to do with K, but we don't know how to replace omega. So what do we use for omega in this case? The idea is, if for K we use the difference in wave vector, for omega we use the difference in energy divided by h bar. So the idea is to replace omega with the energy of electron 1 minus energy of electron 2 divided by h bar. So at this point, the conclusion is that here we need to consider, so we have energy of electron 1 minus energy of electron 2 divided by h bar, and this is squared minus square of the plasma frequency of the dressed ions. And here above we have the E1 minus E2 divided by h bar squared. So this is the, let's say, effective term that we need to consider in the electron-electron interaction when we consider both the electronic and the ionic contribution. Please note this this difference here, in the sense that this is the, let's say, this is the difference in energy between two electrons. Again, the difference in energy between two electrons, and here you have the square of the plasma frequency of the dressed ions. What is the order of magnitude of the square of the plasma frequency of the dressed ions? That will be, let's say, similar to the frequency that we have obtained for phonons. So the idea is in that in general, if you consider the energy difference between two random electrons that you may pick up in the system, that energy difference, I just changed page. Yeah, what we know is that if we just concentrate on that term, we have E1 minus E2 squared. I have just, let's say, removed the H bar from the parentheses and taking that out of the parentheses. So in this way, I have H bar in front of the frequency. And in this situation, this is of the order of phonon, of the phonon energy. So in general, E1 minus E2 is larger and larger with respect to H bar. Plasma frequency of the dressed ions. So if this is the leading term, then this is nearly 1. So you have that the term at the numerator here and this term at the denominator are the strongest one. So you may neglect the second term related to the plasma frequency of the dressed ions. And at this point, this ratio is nearly 1. So the point is that in general, the contribution of the ionic contribution or dressed ion contributions to the dielectric constant can be neglected. But there is an important situation, and that situation is the following. What if E1 minus E2 is smaller than H bar omega plasma of the dressed ions? So, in other words, what happens if the energy of the two electrons that are interacting are very close with each other, so the difference is nearly zero or very, very small? In that case, E1 minus E2 minus squared minus H bar squared omega P squared is smaller than zero. So if that is smaller than zero, then the effective potential is negative. If the effective potential is negative, this means that the electrons are affected by an attractive interaction, not by repulsion. Because in general, the electrons have a repulsive interaction because they have the same charge. But in this specific situation, the electrons have an attractive interaction. So they feel positive. So they feel an attraction that tries to, let's say, bring one electron closer to the second one. So what is the physical motivation behind that? And this result is called over-screening. So you have an excess of screening. That excess is such that the interaction is no more repulsive, but is attractive. And the explanation of that is the following. If you have the lattice, so if this is the ionic lattice, and you have one electron traveling through the lattice, then you have a negative charge close to the ions. So the ions are attracted by the negative charge. Due to this attraction, in this region, you have an excess of positive charge density. due to that excess of positive charge density, a second electron may feel an attraction to that region. So the positive interaction between the electrons is mediated by phonons. So the point is, the electron induces a distortion on the lattice. That distortion may produce an accumulation of positive charge. That accumulation of positive charge may interact with another electron. But since the positive charge accumulation was induced by the first electron, at this point you may consider that the first electron has attracted the second electron. But this process is mediated by phonons. And this result is at the basis of the superconductivity. So in superconductivity, we have that this coupling between the electrons produces, induces in the system a phase transition, and after this phase transition, a large number of electrons are interacting with each other thanks to this attractive interaction, and they give rise to a superconductor in, let's say, okay, nearly no time. But the idea is that if the coupling between this electron and this electron is strong enough, then no impurity, no defect, no scattering will destroy that couple of electrons. And if you are not able to destroy that couple of electrons will travel through the system without feeling the effect of any scattering event. So they will be able to move in the system without with infinite conductivity. So that's why this mechanism is at the base of superconductivity. Okay, and superconductivity will be discussed. A very brief introduction to superconductivity will be included in the next lessons that I will record and then share with you through the classroom. Okay, I just take the occasion to summarize a couple of things in view of the examination as I'm waiting that Professor Moretti comes here. So I just recall you that for the examination, I will not fix official dates. So please do not expect to see official dates on the exam system, but I just wait for you to let me know when you're ready to take the examination. Then we may arrange for a date and the time for the examination itself. So again, please let me know when you're ready for the examination so we may agree for a date. Please remember that the first question of the examination is at your choice. So you may decide what is the first topic that may be useful to start the examination. Please consider that the fact that you have this first topic at your choice doesn't mean you may speak for an hour about something. You're supposed to have just 10 minutes to discuss about this topic of your choice. The idea of this question, of this free question, is just to see whether you are able to choose a topic, discuss about that in a short amount of time. So if you are able to organize things, organize the subtopics with the equations, graphs, whatever you need, so to discuss something and present that to me. Not real presentations, so please do not build up PowerPoint presentations and so on, just using the Blackboard if there will be the opportunity, or a sheet for the examination. So just to write down that. After this first question, then it's a typical oral examination. So I will ask you something and then we may discuss about that. Please keep the examination as a discussion. Consider that as a discussion. So it's not a quiz. Even if you, let's say, I do not expect you to reply in a couple of seconds to the question. You have time to think about that. So it's a sort of discussion about the topics of the lessons. Other thing, during these lessons, we have touched many different topics. So the first, maybe one may see all the lessons as a combination of topics. Each topic is in a box, and the box are not communicating with each other. But this is not the case, since we have also always discussed about electrons, ions in all the different parts of the program. So please try to consider the topics of this lesson as, let's say, a big initial topic, that is the properties of the solid state. And then we have seen from time to time the properties of the solid state using different approximation. So please try to consider the solid state, all the topics that we have discussed in these lessons as part of a bigger subject, that is the properties of the solid state, not as a combination of independent subjects. This is also a part of the evaluation. So one of the things that are evaluated during the examination is the capability of the student to, let's say, connect also topics that are different with each other, and find similarities, differences, or connections. So some of the questions will regard also the connection between different topics, so to see whether you have a clear picture of all the parts of the lessons or not. So this will be a part of the evaluation process. In case from now up to the date where you decide to take the examinations, you have questions, comments, or something to ask concerning what was told during the lessons, please do not hesitate to write me an email, so we may arrange for an appointment in case you have many questions, or you may anticipate the questions to me by email, so that, say, if the discussion can be handled in that way, we may do that. Otherwise, we may set up a meeting, so we may discuss about, I don't know, the points you want to discuss about after you have studied, or you have started to study for the examination. Do you have questions or comments, or something to ask?
It's okay, thank you.
Okay, so now I switch off the connection because Professor Moretti is here, and I will send you an email as soon as the additional part will be uploaded in the classroom. Okay, so goodbye, and hope you. Since I think this is the last question we see directly, I take the occasion to wish you a Merry Christmas with your family. Hope you are all fine, and let's hope to have an Happy New Year. So goodbye, and see you at the examination or before in case you have questions.